For part C, we again have a point and a derivative, and then we ask for another output on the original curve. So we're going to be able to write y of x for any value will be the y we start with, which is 0, plus the accumulation from when we had that output up to x on the derivative function. I'm going to pull that 8 out in front. And write our integrand in terms of t. So now we need to choose our u so that the derivative is also in there, and it will create a derivative that's easy to go backwards on. So I can see here that choosing a sine will generate a u cubed, and the derivative of the sine will cancel out that cosine. So that's a good choice for my u. So I'll let u equal the sine of t, which means dt will be du over the cosine of t. And if I do the replacement, I will get a u cubed times a cosine of t times a du over a cosine of t. Now let's keep in mind that we can change the limits because we have a definite integral. So if I plug pi over 6 into u, I get the sine of pi over 6. That's the y coordinate on the unit circle when I've gone pi over 6 up. So that y coordinate is a 1/2. And the upper limit will be plugging x into u. That will give me a sine of x. So if I now cancel my cosines and answer the question posed by what's left, I get, what did I take the derivative of with respect to u that gave me u cubed? And the answer to that is u to the 4th over 4. And I'm evaluating from 1/2 to the sine of x. So if I plug in sine first, I get sine to the 4th over 4. If I plug in a half, I'll get a 1/2 to the 4th, which is a 1/16 over 4, gives me a 1/64. So this is equal to the definite integral right here. And now I'm going to multiply it by 8. So I'll have 0 plus 8 times this is 2 of those sine to the 4ths, minus, and 8 times a 1/64 gives me a 1/8. Now that's y for any value of x. I'm interested in what comes out of y when I plug in a pi over 2. Well, the pi over 2 is a 1 when I plug it into the sign. So a 1 to the 4th is still a 1, times 2 gives me a 2, minus an 8th, that's a 16/8 minus a 1/8 gives me 15/8.